Of today's presentation, laser welded coated core steel sandwich elements. The presenter, let me see, presenter will be Peter Nilsson, and those participating will not be shown in the recording unless you ask a question at the end. So I give the word to you, Peter.
Thank you very much, Kersti. Well, as Kersti said, my name is Peter Nilsson. I'm here at the company WSP. I'm also a industrial PhD student at Chalmers University, and I work with a new type of steel bridge decks. So the topic of today's presentation will be laser welded corrugated core steel sandwich panels for bridge application. And we are a team at Chalmers working with this project, and it's my supervisor, Professor Mohammad Al-Emrani, and my co-supervisor, Rasul Atashipur, and it's me, and I'm a PhD student also working in this project. So today, my plan is to approximately present the work that is written down in my licentiate thesis that I presented in the end of December, and that will be the work that is in that thesis I will present here today. And of course, I would also like to welcome you all to this presentation. We'll start off by an introduction. When it comes to steel bridge decks, mainly we use them for cases where a low structural weight is of the outermost importance. And in Sweden and this region, we use them particularly for openable or movable bridges, and also for very long span bridges. And the reason why we use them only for the few cases is, you probably can see my pointer here. So this is a typical conventional steel bridge deck, and they are manufactured. Their manufacturing process includes a lot of manual welding, causing the production cost to be high. And furthermore, they consist out of several complex welded joints, which in many cases have led to fatigue cracking and premature deterioration, as you can see down here. And also, these bridge decks have a low stiffness in this transverse direction, causing local curvature in the deck plate, which in turn causes the pavement to crack, which leads to a large cost for refurbishment. So a possible next generation of steel bridge deck is this sandwich solution, which is produced by laser welding. As we can see here, it consists of two faces, top and a bottom face, and these faces are joined together by a corrugated core. And the key to enable this this geometry is what we call laser stake welding. So we weld from one side, penetrating through this plate into the next one. And here we can see figures from the manufacturing process. So basically, you put this plate on the ground, and you place the corrugation on top of it. You laser weld here from one side into this plate, and you put the top plate on, and then you weld through the top plate into this corrugated part here. And as you can see, this is performed in a fixed a structure for fixturing the plates to enable contact between the plates when you weld, which is essential. So comparing the conventional solution to the sandwich solution, there are two main benefits. First of all, it's the production process. It is by far more industrial, where the welding is done completely by robots. And secondly, the structural performance of the sandwich panel compared to the conventional stiffened plate deck is superior. And this enhanced structural performance comes from it originates from three things. First of all, in the stiff direction of the panel, which is in the direction along the corrugation here, you have a shift of the neutral axis, causing more material to have a distance to the neutral axis, increasing the bending stiffness. This is what we refer to as the sandwich effect. Secondly, we have the sandwich panel compared to the conventional panel has a much more pronounced plate action, meaning that it carries the loads in two directions compared to the stiffened plate, which mainly transports loads in one direction. And last, the shear lag effect, meaning the distribution of normal stresses in the deck when it's utilized as a flange, is much less pronounced, causing a more evenly distribution of the longitudinal stresses, meaning that more of the deck is acting as a flange. So these sandwich decks can, of course, be used in movable bridges, which we have performed some case studies on. And we could see that it's possible to reduce the total material of the bridge by 30%. And in this case, of course, the deck itself was lighter, but we could also remove every other transverse girder, reducing the amount of needed welding. One could also think of using these decks in medium span bridges, where we today mainly, at least in Sweden, use steel and concrete composite bridges, meaning that you could replace the concrete deck by a steel sandwich deck. And in a case study that we performed for this, we showed that it's possible to launch the bridge with the deck and the railings and everything in place without having the launching stage being determinate for the geometry of the bridge. So this is a very attractive solution, especially for urban areas where a reduced production time or reduced on-site erection time is of outermost importance. Furthermore, one could think of using these decks in long span bridges, and also there's been proposals in the literature for using these decks in short span bridges where you don't have girder, is just a deck, and it's completely pre-manufactured and lifted in place. So, looking at our research project, I'm going to give you a short overview. When we started this project 3-4 years ago, we thought that production is essential, and we would like to show that it's possible to produce these panels with the laser welding technique, with the thicknesses and the geometry that is needed for a bridge. So this we have done, and we have taken these panels and we have performed experiments both with static loading and cyclic loading. And the panels that we wanted to produce, they have cross sections relevant for a bridge, for application in a bridge. And we performed optimization analysis in order to find the appropriate core angles and thicknesses of the different constituent members. And in order to perform these types of optimization analysis, you need analytical models. So we have also performed some work developing analytical models. And to ensure a sufficient fatigue life of the bridge deck, we have performed detailed numerical analysis in terms of effective knot stress. And as I earlier mentioned, we have done several analyses with respect to the life cycle of the bridge. So today I will talk a little bit about what is in about the research that's included in my licentiate thesis, and this thesis had two separate objectives, or areas of objectives. And the first one is referring to structural analysis methods, due to the fact that if one wants to design or optimize this type of panel, full 3D numerical analysis is very time-consuming, because you need we have a lot of individual members that needs a number of elements per part, inducing a massive amount of degrees of freedom. So it's preferable if this is possible to do with a simplified approach in order to enable design and optimization. And the second objective of this thesis refers to the production-induced variation of the joint geometry, meaning that when we produce these panels, the core-to-face joint, the geometry of the core-to-face joint will not be ideal, and we wanted to investigate how the spread of these geometric properties affect the stresses that determine the fatigue life of the panel. So with respect to structural analysis, we started by investigating the behavior of the panels in the direction perpendicular to the corrugation. And for that reason, the analysis that I present here today is two-dimensional analysis of the transverse cut of the panel. And the reason why we start with this is that in the longitudinal direction, things is a bit more well defined, and this is definitely the tricky part of this of the structural analysis of these panels. Starting to investigating this, we saw that there was a need for some work with respect to the shear stiffness of the panels in this direction. So for that, we developed an analytical solution for the transverse shear stiffness. And this transverse shear stiffness can be used in order to predict the stresses not only in two-dimensional beams, but of course also in panels, in three-dimensional panels. When we looked a bit further into this, we saw that there was a need to include a weld region rotational spring, meaning that the weld that connects the core to the face is not ideally rigid or ideally a hinge. It's in practice somewhere in between. For that reason, we made an investigation about this, and we derived a closed form solution for the rotational spring stiffness of the weld region rotational stiffness. So we have two separate objectives of the thesis, and I will start by looking at the things that refer to the structural analysis. And as I said before, when it comes to design and optimization of these panels, full 3D analysis, numerical analysis, is too time-consuming for both optimization and design, due to the fact that when we design a bridge, we need to consider a lot of different loading situations. We have several different types of vehicles, and the vehicles should be able to be positioned at any position of the bridge, meaning that we have to iterate this structural analysis a lot of times. So if it's possible to homogenize this plate, meaning that we define the stiffness properties of the panel, and we analyze it as one single layer plate, then we would reduce the analysis time hugely, and it enables a design process and a optimization process. So this homogenization means that we start in the first step to analyze the discrete structure, and we establish the equivalent stiffness properties of the panel. And then we perform a structural analysis of the single layer panel with the homogenized stiffness properties, and from that we get a deflection field, and from the deflection field we can calculate the sectional properties of the panel. There's the sectional forces and moments of the panel. And when we have those sectional forces, we can apply them to the discrete structure here in a analysis. And from this calculations, we can establish stress distributions in the constituent members of the discrete structure of the panel. Of course, when one performs this type of homogenization, you miss the effect of the fact that you have a load directly applied to the structure that causes local curvature of the panel. However, the work that I present here so far, we exclude these effects and look strictly at the homogenized response of the panels. And as I mentioned earlier, we have a focus here on the weak direction of the panel, meaning the direction perpendicular to the core. When it comes to shear in this weak direction, there exists a couple of analytical expressions in the literature. However, all the existing analytical derivations are restricted to a single connection between the core and the faceplate. And early on in our work, we saw that we have to use 2 welds in order to ensure fatigue relevant stresses that are low enough to ensure a proper fatigue life of the panel. So we need at least to have 2 connection points between the core and the face. This means that there was a need for a new analytical solution. So we derived this, and this was presented in a paper that is published in Thin Wall Structures, and this is paper 1 of my licentiate thesis. So this analytical solution that we derived, it incorporates 2 welds in the connection between the core and the face plates, and furthermore, it includes a weld region rotational spring. And what is this weld region rotational spring? Well, when we manufacture these panels, the manufacturing process will induce some sort of gap between the faceplate and the core. And the connection will not be either a hinge, or it will be perfectly rigid. So it will be something in between. So the analytical solution, it needs to incorporate a rotational stiffness of this region, and that we incorporated in our model. And this is the structural model which is the basis for the derivation. And the derivation is based on the direct stiffness method, and in order to derive the stiffness of this curved corrugated core, we used an minimum potential energy theorem. And this is parts of the analytical expressions, and I will skip the details of this for now. But what we see here is on both pictures, of course, this method or the analytical expression that we derived here, it doesn't only include the transverse shear stiffness. You could also use it to, from a known shear force, you could calculate stresses in all the constituent members of the cross section. And on the left here, we see the normalized transverse shear stiffness, which is the where the lines are the analytical expressions that we presented in this paper, and the circles are validating numerical analysis that for validation of our analytical model. And we can see here that they are in perfect agreement, both when it comes to predicting the shear stiffness, but also when it comes to predicting stresses from a unit shear force. So, and on the x-axis here, we have K, which is this weld region rotational stiffness. And one could also notice that this weld region rotational stiffness has for these 4 different cases, quite a modest impact on the transverse shear stiffness, but it has, in some cases, a higher impact on the stresses. This is the top face stresses in the vicinity of the weld on this right figure. And as I mentioned earlier, we saw also a need to derive a closed form solution for the weld region rotational stiffness, and we did that by using an approach including a large number of numerical analysis which we post-processed with linear and nonlinear regression analysis to come up with this. Here we have the rotational spring stiffness as a function of these four geometric properties, which are the thicknesses of the two plates, the weld width, and also this possible gap between the plates. So in order to find this closed form solution, we executed a 4,000 numerical analysis, varying these geometric properties with plate thicknesses between 4 and 16 millimeters, weld widths between 1 and 4 millimeters, and plate gaps between 0.1 and 1 millimeter. And then we found this very simple expression here for the rotational spring stiffness. And we could see that when comparing each individual finite element run and the closed form solution, we could find maximum errors here of approximately 7%, but these are very rare cases, and actually they are all of these cases here, which are above 3%, are for cases that are not really or in the very on the boundary of the practical range. So in general, there is a for all of these 4,000 runs, the closed form solution predicts the rotational spring stiffness approximately with an maximum error of 2%. And to also in this, and I should also say that this work with respect to the rotational spring stiffness was presented in a conference paper from the Eurosteel conference, and it's the second paper of my licentiate thesis. So in my thesis, I also show that it's possible to perform a one-dimensional homogenized beam solution which predicts stresses in all of the cross-section. And in order to validate this, I have compared 3 different levels of modeling. First, it is this one-dimensional analytical solution, and then I compare it with a 2-dimensional frame solution, and then also with a 2-dimensional continuum solution. And comparing these, and now we see top phase stresses, and the load case is here. As we can see, we are investigating this area and the top phase, so it's the stresses along this part at this position, and we can see that we are away with a distance both to boundary conditions and to loads. So we are investigating the effect of global load effects. Here, in this figure, I compare a 2-dimensional frame analysis to the 2-dimensional solid analysis. And I can see that they are in very good agreement, apart from here at the exact position of the welds, which of course reflects the fact that in the 2-dimensional solid analysis, we include the effect of the plate thicknesses, and which we don't in the frame analysis. But apart from that, they are in perfect agreement. And here I compare the one-dimensional beam analysis to the two-dimensional frame analysis. And when I calculate the stresses in the top phase here from the beam analysis, which is the solid line, I have used our developed transverse shear stiffness, and I have used classical sandwich theory for calculating the stresses from the global bending moment, meaning that the faces, the outer faces, carries the stresses alone. And we can see that in this region, which is here, when we move away from the weld, we have a good agreement. However, at the welds, we can see that there is a slight discrepancy. Which doesn't have a major effect on the top phase stresses. However, there is a difference here when at the position of the weld, which shows that when this method is used to calculate the stresses in the weld itself, there will be a discrepancy. So we know that we have verified our transverse shear stiffness model, so this discrepancy must refer to the stresses coming from the global bending moment. So in order to account for these, I performed a separate numerical analysis to calculate the stresses from the bending moment. And then the one-dimensional analytical beam solution is in perfect agreement with the two-dimensional frame analysis, which then shows that it's possible to calculate the stresses in the constituent members in the weak direction of a corrugated core sandwich panel by using only homogenized analysis. And in order to validate our models further, we performed some experimental validation, and we executed the exactly same case that I showed you before, and we equipped the beam with strain gauges, and here are the results, where the solid line is the two-dimensional solid solution, and the points are from the experimental study. And we can see that we have a good agreement here, moving away from the weld. But here, at the position of the weld, we had a special strain gauge, which we had a special device which included 10 strain gauges with a very short distance between the gauges. And the idea was to monitor the stresses at this position very accurately. However, at this position, there is a discrepancy between our analysis and the experimental results. And whether this originates from that the structural analysis lacks in some way, or if there was a problem with the measurements that has not been completely evaluated yet. So that is some work yet to come. So from the structural analysis point of view, the conclusions are that the new analytical formulation for the transverse shear stiffness can accurately predict both stiffness of the cross-section and stresses in all the constituent members of the cross-section when it's subjected to transverse shear forces. And the closed-form solution for the rotational weld stiffness can predict the stiffness with a high accuracy when compared to numerical analysis. And the presented homogenized beam approach is shown to be accurate if the effect of bending is considered by a refined model. So for the second part of this licentiate thesis, we investigate the joint geometry. So what we want to see here is the effect of the production-induced geometric variation of the coarse-to-face joint on stresses which are relevant for the fatigue life of the panel. And in this project, we produced 4 panels, 2 out of conventional structural 355 steel, and 2 out of stainless duplex steel of the quality LDX 2101. And the panels have a slight different cross-sectional geometry. And they are approximately 2 by 2 meters. So in order to perform this investigation, we measured the joint geometry. We cut the panels into beam sections, and we measured the core-to-face joint. The 3 parameters that we have investigated is the weld width, it is the gap between the plates, and it is the misalignment of the weld line. And this misalignment, the distance between the 2 weld lines is very close to constant, because this is welded by robots and they are very exact, luckily. However, there could be a slight discrepancy between the direction of the weld line and the corrugation line. And this causes a misalignment of the weld pair in comparison to the to this flat part of the corrugation here. So the weld pair has moved closer to the corrugation leg here. So these 3 parameters we wanted to investigate. So we measured them and we quantified these, and we could see that the weld width is in general between 1 and 4 millimeters for these specific plate thicknesses and this specific weld process that we used. And we could see that there is quite much larger scatter when it comes to the gap between the plates, and the gap is ranging from full initial contact to up to approximately 1.5 millimeter of plate gap. And the weld misalignment in general varied between 1 and 3 millimeters. So in order to investigate this, to see how these this production-induced geometric variation affects the fatigue-relevant stresses, we performed a parametric study including a large number of finite element analyses. So we investigated 3 different beams with different geometric properties. We included 2 different types of load situation. One here on the left, where the global action is restrained. So this is has a much more pronounced local action, which then is something that simulates the curvature of the plates when it's subjected to a wheel pressure load. And then on the right here, the second load case, which we are evaluating this region, which is highlighted here. This second load case, this region is subjected to or this cell is subjected to pure global action, meaning that it has a global moment and a shear force. So going straight to the conclusions of this parametric study, we could see that for the case of pure global action, this weld misalignment has a considerable effect. Having a 2 millimeter weld misalignment could increase the effective notch stress at the weld by up to 40%. So this tells us that this weld misalignment is something that is important to have strict tolerances on when it comes to manufacturing. And secondly, we could see that the gap between the plates, because we executed all analysis, both including and excluding contact. With contact in this region that we see here, in this region. And we could see that the gap of itself in its own, when we don't include contact, it has no effect on the fatigue relevant stresses. However, the gap is the main factor controlling at what load magnitude do we have contact between the plates. And for that reason, when we include contact, the gap has a major effect on the weld stresses. And for this load case, which is referring to the local curvature, the fatigue relevant stresses always decreased when we have contact. However, for this case, when we are looking at the case with pure global action, the fatigue relevant stresses could for some cases increase when we include contact in our analysis. So this tells us that contact is something to be observant when it comes to fatigue design of these panels. And the third main conclusion that is included in this third paper is that increasing the weld width, the size of the weld, could either increase or decrease the fatigue relevant stresses. And the reason for this is that the weld width in turn affects several different phenomena. Of course, increasing the weld width increases the sectional modulus of the weld itself, meaning that we reduce the stresses. However, we also increase the interaction between the core and the face, which increase the stresses. So for some cases, increasing the weld width could increase the fatigue relevant stresses. And those were the main conclusions from the third paper of the thesis, which is not yet published, but this paper is submitted to the journal Welding in the World. So for future work, we would like to, as we saw that the bending moment in this transverse direction has a effect on the stress magnitude in the welds, there is a need to develop a bending analytical solution for the bending stiffness for our corrugated core with dual or double weld lines. And we also need to include the effect of directly applied load into our design approach. And of course, the methodology that I showed was on beams in the transverse direction or the weak direction of the panel. This needs to be extended to a full 3D into a panel level. And of course, when it comes to steel bridge deck, fatigue is highly relevant, and there is a need to perform fatigue tests and investigate the fatigue strength when it comes to this specific geometry. And to give you this was the conclusions and the future work when it comes to my that was included in my licentiate thesis, but there has been about a month of time, so we have of course already started with this work, and I will give you a little glimpse about where we are at right now. And this is when it comes to the structural analysis. Here we can see in the plot here, it's a comparison between a three-dimensional a reference analysis, which looks something like this in mesh density, and we compare it to the solution of this developed enhanced homogenized approach, and we include the effects of the directly applied loads and bending moment and shear in all directions. And here we can see a comparison that if this is done using this approach, we have a very nice agreement. However, this is preliminary, and it's not it has not been validated in detail yet. That was structural analysis part, and when it comes to fatigue, we have some ongoing tests. On the left here, we can see fatigue tests on a panel level, 2x2, the 2x2 panels that I showed earlier. We have tested those, and we used up all our time in the lab. So we got kicked out, but as soon as we get some more time in the lab, we will continue, because they had a higher strength than we calculated. So we need to execute a lot more loading cycles for these ones, for the panels. So that will be done here during the spring. We will continue this fatigue testing during the spring. But this is done on two specific plates in order to show the behavior, what happens when we get the fatigue crack, where does it appear, and how does the fatigue crack propagate. And in order to get a statistical basis to derive a fatigue strength that we can use for design, you have to execute a large number of tests, and that we do on small scale specimens. And this is a figure from how it looks in the lab today, where we have just started the fatigue testing series. And that was what I planned to say today. And of course, I have some people to thank that are supporting this project. Of course, Statens vegvesen and the program of Coastal Highway Route E39. And we have also support from the Swedish corresponding organization Trafikverket. And we have had a research project from Swedish Research Council, Vinnova, which is now closed, or which was called InnoDefab, with a large number of industrial partners. And of course, we always thank Klevenwerft for supporting us with producing laser welded sandwich panels that we have, the test specimens that we have used in our lab. So that was the last slide.
I have sent you some questions. Do you see them on your screen?
Now I do.
So the questions are, how will your work help us in producing safer constructions in the E39 project? Will it give us lighter construction, longer lifespan?
Yeah, it's if you incorporate this technology, you would be able to produce, for example, box girders that utilize less material, and they utilize less material, and they are the amount of manual on-site welding is also reduced, which is also important. And from that perspective, one maybe could say that also the construction could be safer. But it's more on the economical and environmental parts of sustainability with reduced cost and reduced used material. That's the two main parts. And we have a question: longer lifespan. Well, the lifespan is what we design for. So one could say that you could have the same lifespan as a conventional solution, but with less material. We have a question. Weld misalignment. What impact can that up to 40% have on a long construction? Well, that those increased 40% is for a specific case. So whether that is decisive or not, this investigation doesn't tell us. So we don't know if this 40% actually causes us to use more material. But it tells us that when we have a case of close to pure shear or at least just global sectional forces, the stresses that determines the fatigue life will increase by up to 40%. So whether this is decisive or not, I cannot tell without doing a detailed design. Can it be leveled out, or will it be worse if it happens in several places? If this is corresponding to this 40%.
That was part of the first or the.
Yeah. So I think I answered
Yep.
that question as well there. So it's those 40% is a specific loading case. It's Professor Milan Velkovic. Thank you. Fortunately, these small-scale tests has just started. So what we have done with the small scale test is that we have found a theoretical load level which gives stresses that would give us approximately 2 million load cycles. So we are in a that tells us that we are in a relevant loading level. But more detailed analysis and comparison between the small scale and the larger one, we haven't come to that yet. But I am quite sure that we will. In 2 years, it's time to present a doctoral thesis, and by then, I hope that we have some nice correlations in this area of fatigue between the small scale and the larger scale specimens. And also in that thesis, I hope and believe that there will be a full methodology that can be used for design and optimization structural analysis of these panels. I hope that was an answer to your question, Milan. And I can see that
this is just me reminding of the next presentation that is coming up.
Yes, perfect. Yes, of course, Milan, and as always, thank you for your input.
Okay, and thank you, Peter, for a very nice presentation, and we will be very interested to hear more about your thesis and more about your work, and of course, we hope that you will get back in the lab soon.
Yes.
Mohammed is congratulating you.
Yeah, and he has a question. Maybe we can take that as well. What about the cost reduction? What could we expect based on reduction for material and production? Yes, that depends on the case. I cannot make any statements when it comes to these, if this technique should be incorporated in a very large scale box girder. But we could see from this Bascal bridge that we examined, and for that case, the amount of material was reduced by approximately 30%, if I remember correctly, and the costs were reduced by 25% compared to the conventional solution. And from that reduction of 25%, half of that cost decrease originated from reduced amount of material. The other half originates from the fact that you have less details to weld manually, and the details are less complex because you don't have to do this welding in this or non-min that you have in the conventional solution. So you have reduced amount of material, and you have less manual welding and less complex welding. And looking at the large-scale box girders, I would think the main benefit would be to reduce the weight, but also the possibility to have longer between two diaphragms. That would affect the costs in that type of project, I think. Yes. What more needs to be done before this can be put into use. Well, design codes. I would say that when it comes to implementation of this technology, then of course the needs to be in place. So we need to perform the testing the small scale test that we are doing now, and probably I think I have about 40 test specimens and with load levels to get different stress levels, but there probably would be a need to perform some additional fatigue testing to get a more generic detail category. So this, however, when it comes to manufacturing of these, I don't see many new things that we need to, because if we use strictly laser welding, pure laser, so we have no combined hybrid welding processes, then the production process or the welding process is defined in a European standard. So that should be possible to use. However, I know that if one would like to use this in a Swedish bridge, there is, as the technique is not used, there is a lot of points or demands on the panels that needs to be thoroughly investigated, and that is, I think the toughest question would be, or the toughest part would be, how to repair if there is a crack somewhere, and we need to replace a part of the deck. That would cause. That's an area that needs some additional thinking on how to do that. As you have this sandwich cross section, so those things I think are the parts that's obstructing implementation. But when it comes to structural behavior, it's fatigue that is the missing link. I'm not sure if that was a good question, but I hope it was good enough, Matthias.
Okay. Then I think we will say thank you. And as I mentioned, you're welcome back next time, all of you. And then I will stop the recording. Thank you.